Hello chemistry students, this is Dr. Tullis. We are going to start talking about entropy and do a little bit review on thermodynamics as we cover the first 3 sections looking at entropy. Here are many of the learning objectives we will cover in the 3 sections. But first, let's look at some thermodynamic concepts that we covered in General Chemistry 1. The system and the surroundings. So the system is the part of the universe that we are looking at, or that's under study. The surroundings is the rest of the universe that's outside of the system. We have exothermic and endothermic reactions. In an exothermic reaction, energy transfers as heat from the system to the surroundings. So heat is evolved by the system, and it is a negative delta H. An endothermic reaction is when energy transfers as heat from the surroundings to the system. So heat is absorbed by the system. Therefore, we have a positive delta H. The first law of thermodynamics, the law of conservation of energy, that energy cannot be created or destroyed. The change in internal energy of a system is the sum of energy transferred into or out of the system as heat and or work. So the first law of thermodynamics says that delta U is equal to Q plus W. We have standard conditions. That means that we have a pressure of 1 bar or 0.98692 atmospheres. We have the standard enthalpy of formation, the enthalpy change that occurs when 1 mole of a compound is formed from its elements in their standard states. Continuing with our review, heat is energy that moves into or out of a system because of a temperature difference between the system and the surroundings. We know heat always flows from the warmer to the colder object. Work, on the other hand, is the energy exchange that results when a force, F, moves an object through a distance, d. So work is equal to force times distance. Remember the signs. If work is done by the system, then our work is negative. If work is done on the system, then we have a positive work. Still looking at the review, enthalpy change, which is that delta H, is the energy transferred as heat under conditions of constant pressure. In practice, we measure certain heats of reactions and use them to tabulate enthalpies of formation. Standard enthalpies of formation for selected compounds are listed in the back of the book. And the standard enthalpy change for a reaction is when we take the sum of the enthalpies for the products and minus the sum of the enthalpies of formation of the reactants. And then we have a state function, which is the property of a system that depends only on its present state, which is determined by variables such as temperature and pressure, and is independent of any previous history of the system. Here's the new stuff. In chemistry, we encounter many examples of chemical changes or chemical reactions and physical changes like the formation of mixtures, the expansion of gases, and the changes of state. Change is central to chemistry, so it is important to understand the factors that determine whether a change will occur. Chemists use the term spontaneous to represent a change that occurs without outside intervention. There is an important observation to be made. Spontaneous changes occur only in the direction that leads to equilibrium. So spontaneous is a term for a naturally occurring change. It has a tendency to occur without being driven by an external influence. Spontaneous changes don't need to be fast. An example would be if you put your hand on a hot cup of coffee, that heat is transferred from the cup to your hand. That's a spontaneous change. A non-spontaneous change would only occur if it's driven. It would be like a coffee pot heating up. It would need to be placed on a stove, and energy would need to be forced into that. Here are several examples of spontaneous processes. The solvation of a soluble salt. Let's say I took ammonium nitrate. It dissolves spontaneously. It's an endothermic reaction. The expansion of a gas and diffusion when gases mix to form homogeneous mixtures spontaneously. Certain phase changes like ice that melts spontaneously when it's sitting out at room temperature, or water that evaporates. Certain chemical reactions. Sodium, solid sodium metal, reacts vigorously when dropped in water, and iron rusts when exposed to the atmosphere. Those are certain chemical reactions that occur spontaneously. So think back to when we talked about thermodynamics. Thermodynamics is the study of the relationship between heat and other forms of energy in a chemical or physical process. Enthalpy alone does not predict spontaneity. Now, some processes are energetically favored, but they're not spontaneous. Like two objects at different temperatures that are placed in contact, heat will flow spontaneously from the hotter object to the colder object. There is a dispersal of energy, but no net change of energy. Equilibrium alone cannot determine spontaneity. Some processes are favored based on equilibrium, but they are non-spontaneous. There must be another factor that plays a role in the determination of spontaneity. So the factors that affect spontaneity: enthalpy and entropy. Enthalpy is the comparison of bond energy, and entropy is the randomness versus the order of a system. Enthalpy is denoted with a delta H. Entropy is a delta S. In general, enthalpy is more important than entropy. This is the first time we've seen this variable S. There is a state function called entropy that allows us to quantify the disorder and dispersal of energy. The second law of thermodynamics states that a spontaneous process is one that results in an increase of the entropy of the universe. So delta S is greater than 0. Probability suggests that a spontaneous reaction will result in the dispersal of energy, so the energy goes from being more concentrated to the final state being more dispersed. Here's an example of entropy in the kitchen. We have a raw egg. It says it exemplifies the asymmetry of time. A fresh one breaks easily, but a broken one does not spontaneously put itself together again, for the simple reason that there are more ways to be broken than not. In physics jargon, the broken egg has a high entropy. Here it shows there is one way to be whole. There are lots of ways to be slightly cracked. We can have a little crack here, we can have a line crack here, and there is a whole bunch of ways to be fully smashed. All sorts of different ways, which shows us the disorder and the dispersal of randomness. We can also look at the entropy looking at low entropy and high entropy when we're looking at H2O. Low entropy would be ice. High entropy would be liquid water. We're looking at highly ordered particles. And when we have an increase in entropy, so more disarray, more disordered, our particles in liquid form are much more spread apart. Again, looking at the disorder of a system, disorder means it has a higher S and it's more probable. Order is a low S. Here's an example looking at these jelly beans. We have low entropy versus high entropy, much more disorder here. We can see that as I go to the right, I have an increase in entropy. There is more disorder as I go from a solid to a liquid to a gas. We can also see that there is a numerical value for entropy that can be determined for any substance under a given set of conditions. For example, I have liquid water versus gas water, and it's given a numerical value. Liquid water at about 70 joules per Kelvin mole, as opposed to gas, almost 190. So we can see that gas has a greater value, and we know that gas has a much greater randomness than liquid. Here's another example looking at bromine. I have liquid bromine and I have gas bromine. And my liquid bromine has a value of 152 joules per Kelvin mole, and bromine vapor is 245. So we can see that gas has a greater S. As the size of your container increases, also we have greater entropy because the number of microstates accessible to the system increases. When our gas expands to go from just one side of this container to having access to both sides of the container, we are doubling the volume, and therefore our entropy increases, the disorder increases. Obviously, like we stated, gas has greater entropy than liquids and solids. It is a state function. We can do the same calculations like we did with enthalpy. If I take my final minus my initial entropies to get my delta S, I can also do the same thing for delta S of the reaction. I can take the entropy of the products and minus the entropy of the reactants. Nothing has a value equal to 0. If it was equal to 0, it would be at 0 Kelvin, and we know that that's not possible. The entropy of a perfect crystal approaches 0, so S would be equal to 0 as the temperature hits 0 Kelvin. And we know that's not going to happen. And negative values of entropy cannot occur. Entropy also increases with temperature. Think as temperature increases, particles start moving faster. And as particles start moving faster, the disorder increases. We can see here that as the temperature increases, my entropy also increases. It increases here as a solid and then shoots up during the phase change as it melts, and then shoots up during a phase change again, and then as a gas. To calculate entropy during a phase change, we simply take our Q divided by the temperature. Q is our heat transferred in the phase change. So if I know that Q for the phase change going from liquid to gas is 40,700 joules per mole, I can take that Q and I can divide it by the temperature at that phase change to get my delta S. We can see here that S increases slightly with T here, but yet S increases a large amount during a phase change. This just shows us some more that we have high randomness, high entropy, high disorder if we were to say that this was a gas phase. All the way down to if this was our solid. We have low randomness, low entropy, low disorder. The delta S of our universe is equal to the delta S of the system plus the delta S of the surroundings. The delta S of the universe is greater than 0 for spontaneous processes. The delta S of the universe is less than 0 for non-spontaneous processes. And the delta S of the universe is equal to 0 for a process that's at equilibrium. We looked at the value of S for a liquid versus a solid, but what about if I looked at two different compounds, magnesium oxide and sodium fluoride? The difference here, we can see that magnesium is a +2 ion and oxide is a -2 ion. Sodium fluoride is a 1-to-1 ratio, +1 and a -1. And we can see here that we have a much greater number here of 51 versus 26 for the +1 and the -1 compound. The greater entropy values on the +1, -1 charges versus the +2, -2 charges. There's greater attraction between higher charges that keeps them from moving. And if it keeps them from moving in those higher charges, that means that it is less disordered. The +1 and the -1, there would be less attraction, and less attraction means that they will move more. Moving more is more randomness, more disorder, and a greater entropy. Let's look more at entropy and the second law of thermodynamics. Because thermal energy is the result of the random motion of particles, potential energy is dispersed when it is converted to thermal energy. This conversion occurs when energy is transferred as heat, which is Q. It is therefore not surprising that Q is a part of the mathematical definition of entropy. In addition, the effect of a given quantity of heat transferred as heat on energy dispersal is different at different temperatures. It turns out that a given Q has a greater effect on delta S at a lower temperature than at a higher temperature. That is, the extent of energy dispersal is inversely proportional to the temperature. The second law of thermodynamics states that the total entropy of a system and its surroundings always increases for a spontaneous process. Therefore, it is greater than 0. As stated in the previous slide, our equation for entropy, delta S, is Q divided by T. QREV is telling us that it's a reversible process that can be returned to its original state, its chemical equilibrium. An irreversible process cannot be returned to its original state. Now, it is important to notice that when we divide by temperature, that it is the Kelvin temperature. Also, the SI unit of entropy is joules per Kelvin, and joules per Kelvin mole to include the mole. And it is a state function. Entropy is a measure of the extent of energy dispersal. In all spontaneous physical and chemical processes, energy changes from being localized or concentrated to being more dispersed or spread out. In a spontaneous process, the change of entropy, which is denoted as delta S, of the universe, indicates the extent to which the energy is dispersed. So far, however, we have not explained why dispersal of energy occurs. So in order to do this, we need to consider energy in its quantized form and matter on the atomic level. Let's consider the system in which initially there is one atom with 2 packets or quanta of energy and 3 other atoms with no energy. So in this case, I have one particle with 2 circles around it, so that's our 2 packets of energy. And then we have 2, 3, and 4 with no energy. Let's say that we have collisions among these atoms, and it allows energy to be transferred so that over time all distributions of the 2 packets of energy over the 4 atoms are seen. There are 10 different ways to distribute the 2 quanta of energy among the 4 atoms. Each of these 10 different ways to distribute the energy is called a microstate. There is a distinct preference that the energy will be dispersed over a greater number of atoms. Let's look at those options. I could have both packets of energy being on the first particle. I could have both packets of energy being on the second. I could have both being on the third, right here. I could have both being on the fourth. But there is a greater chance that it will be dispersed among other particles, like here. That one packet would be on particle 1 and one would be on particle 2. Or that one would be on 1 and the other would be on 3. Or that one's on 1 and the other's on 4. Let's look at some other options. If it's not 1 and 2, 1 and 3, 1 and 4, it could be 2 and 3, 2 and 4, and the last option would be 3 and 4. So notice we have 1, 2, 3, 4, 5, 6 options, where the energy is dispersed amongst the atoms, where it's not just both on the single atom. So a microstate is a specific configuration of the locations and energies of the atoms or molecules that comprise a system. For processes that involve an increase in the number of microstates, we say that that entropy of the system is positive or favorable. If we have a process that reduces the number of microstates, then the entropy of the system is negative or unfavorable. Let's add more atoms to our system. Let's say instead of 4, we have 6 atoms. So I have 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, 6 and 6, when both packets of energy are on the same atom. But what other options are there? The 2 packets of energy could be on 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6. Could also be on 2 and 3, 2 and 4, 2 and 5, 2 and 6. 3 and 4, 3 and 5, 3 and 6, 4 and 5, 4 and 6, 5 and 6. Notice that 15 of the 21 options are when the energy is on 2 different atoms. And here I have 21 possible microstates. All I did was add 2 more atoms, and I went from having 10 microstates to 21 microstates simply by adding 2 more atoms. So as the number of particles increase, the number of microstates available increases dramatically, and the fraction of microstates in which the energy is concentrated rather than dispersed goes down dramatically. It's much more likely that the energy will be dispersed rather than concentrated. And when we say dispersed, we mean here we have 71% of the energy will be dispersed, not on the same atom, compared to here when I had 10 microstates, 60% was dispersed. So we went from 60 to 71. Here's another example of microstates. Let's say that we have a system comprised of n particles distributed among n boxes. We can actually figure out the number of microstates possible by doing little n raised to the power of the big N. For example, if I want to distribute 4 particles among 2 boxes, 2 raised to the 4th power would give me 16 different microstates. Here's one option. I could have all 4 of these particles in one box and none in the second box. I could also have the reverse, none in the first and all 4 in the second. I could also have 3 particles in one box and a red on the right. I could have 3 particles on one side and the green on the right. I could have a blue on the right. I could have a yellow on the right. So that's 4 options. I could also have 2 and 2, and instead of red and green on the left, I could have red and blue on the left. I could have red and yellow on the left. I could then flip-flop everything. I could have blue and green on the left, green and yellow on the left, blue and yellow on the left. Notice that the 2 and 2 options is my most probable distribution because there's 1, 2, 3, 4, 5, 6 different microstates. That's our largest number of microstates is the 2 and 2 options. I could also have the 1 and 3 option, which is the reverse of B, where I had 3 and 1. I could also have the 1 and 3. We're going to have a wild example here. Let's go back to where I had 4 atoms, but instead of having 2 quanta of energy, let's say I had 6 quanta. Assume that we start with 2 atoms having 3 quanta of energy each. The other 2 initially have 0. That gives us 84 microstates. So when I had 4 atoms with 2 quanta of energy, I had 10. Go from 2 quanta to 6, I then can have 84 different microstates. Increasing the amount of energy that is dispersed resulted in a huge increase in our number of microstates. As the number of particles and our quanta increases, you can see that the number of energy microstates grows rapidly. Here are just some options. Let's say that I had my 4 atoms and particle A had 3 quanta and B, C, and D each had 1. And just taking that 3 and 1 option, what if B had 3 and A, C, and D had 1? That would equal 6. C had 3, A, B, and D had 1. D had 3, A, B, and C had 1. And you can see that there are so many other options and different ways to achieve where that 6 quanta of energy is dispersed between 6 different atoms. Now, Ludwig-Boltzmann proposed that the entropy of a system, the dispersal of energy at any given temperature, results from the number of microstates available. As the number of microstates increases, so does the entropy of the system. So he came up with a relationship showing us that entropy of a system is equal to K, which is Boltzmann's constant, this 1.381 times 10 to the negative 23, times the natural log of W, and W is the number of microstates. Using this relationship, we can use that to predict how many microstates are available if we know the standard entropy value of that system. Here are a few other useful equations to find delta S. Entropy also increases as molecular structures become more complex. We can see here that methane, which is CH4, has an entropy value of 186.3. Ethane, which is C2H6, has an even larger value than that. And propane, C3H8, has an even greater value. When a solute dissolves in a solvent, the process is spontaneous, showing us that we have an increase in entropy. And matter and energy are more dispersed, so we have a greater number of microstates. Entropy is higher for things that have higher temperatures, larger volumes, more complex molecules, a higher number of moles of gas, a larger sample size, heavier atoms, gas relative to liquid or solid, and liquid relative to solid. Why don't you pause the video here and tell me which one has higher entropy, NO2 or N2O4, and I2 gas or I2 solid? Well, when I look at NO2 and N2O4, both of them are gases, but the N2O4 is a larger molecule, so it's going to have a greater entropy. And here I have a gas and a solid, so my gas is obviously going to have greater entropy. Pause the video here to see who has higher entropy and explain why. This first one, O3 versus O2, they're both gas, but O3 is a larger molecule, so it's going to have a higher entropy. And here I have tin chloride as a liquid and tin chloride as a gas, so the gas would have the greater entropy. So remember when we said that a perfect crystalline substance at 0 Kelvin has an entropy of 0? That is actually the third law of thermodynamics. When temperature is raised, however, the substance becomes more disordered as it absorbs heat. The entropy of a substance is determined by measuring how much heat is required to change its temperature per Kelvin degree. Hence what gets us this equation. So to determine the value of entropy, it is necessary to measure the energy transferred as heat under reversible conditions for the conversion from 0 Kelvin to the defined conditions, and then use this equation to find entropy. Because it is necessary to add energy as heat to raise the temperature, all substances have positive entropy values at temperatures above 0 K. Now, the standard entropy of a substance or ion is the entropy value for the standard state of the species, also called absolute entropy. And there is a table in the back of your book that has standard molar entropy values, just like there was enthalpy values from Gen Chem 1 that we would refer to. Note that elements have non-zero values, unlike standard enthalpy values of formation. Remember, if I said H2 plus O2, these were always zero enthalpy values, but elements have values of entropy. We do calculate delta S the same way by looking at the sum of the products, and the stoichiometric value of the products comes into effect here, minus the sum of the reactants. Again, we need to know those stoichiometric values. Even without knowing the values of entropies, you can sometimes predict the sign of delta S for a reaction. If, let's say, a molecule is broken into 2 or more smaller molecules, if there's an increase in the moles of gases from reactants to products, and if we can see that a solid changes to a liquid, we can say, oh, then that entropy will be a positive value. Let's set this up. We have hydrogen gas plus oxygen gas to give me liquid water. To set this up, I'm going to say 2 times the entropy value of liquid water minus 2 times the value of hydrogen plus 1 times the value of oxygen. When you look these values up in the appendix of your book, I would find these 3 values, and when I plug it all in, I get a delta S of negative 326.9. And think about it. I went from having gas reactants to liquid products. Going from a gas to a liquid is a negative entropy value. If I went from a liquid to a gas, that's becoming more disordered. That would be a positive entropy value. But I went the opposite way. I also went from 3 moles of gas, 2 plus 1 is 3, so 3 moles of gas to 2 moles of liquid. Here's just a little snippet showing us some entropy values. Here's my H2 gas, here's my O2 gas, and there's my H2O in liquid form, giving me that 130, the 205, and the 69.9 from right here. Using the standard molar entropies from the back of the book right here, calculate the standard entropy change for the following 2 processes. Pause the video here and you try it. For the first one, I took my products, which is my ethanol in gas form, the 282.7, minus the reactants, and there's 1 mole of each, so I looked on my ethanol in liquid form, the 160.7, so products minus reactants, and I got 122.0 joules per Kelvin mole. For the second problem, I took my products, so 2 times NH3, here's my NH3 value, the 192.77, minus all of my reactants, so I did my N2, which was up here, the 191.56, plus 3 times H2's value, so 3 times 130.7, and I got a negative 198.1 joules per Kelvin mole. Notice that for the first one, I went from a liquid to a gas, so I should have a positive entropy value. I became more disordered. For part B, I went from having 4 moles of reactant gas to 2 moles of product. So I did not become more disordered. I became more confined, more organized. So I have a negative. Here's our last example. Pause the video here and try to solve for A and B. Let's check both of these. I got positive values for both of them. Positive 74.95 joules per Kelvin mole and positive 96.09. If I look at this, I went from a solid to an aqueous solution. I became more disorganized, therefore it's a positive value. On part B down here, I have 1 plus 3, 4 moles of gas on the left, and 2 plus 3, 5 moles of gas on the right. So because my mole value increased, I should have a positive entropy value there too. And that wraps up section 3.